Today I am going to introduce a new concept, the concept of analytic functions. I think you are all familiar with complex valued functions. A function, a complex valued function, f of z is said to be analytic at z0 if its derivative exists not only at z0 but at every point in some neighborhood of z0. This is one of the definitions. There are two more definitions for analytic function. A single valued complex differential function is said to be analytic. There is one more definition for analytic function. Let f of z be a complex valued function. Suppose that its derivative f dash z exists at z0. If f dash z is continuous at z0, then f is said to be continuously differentiable at z0. A continuously differentiable function is said to be analytic. If it is further differentiable, that means f2 dash z0 exists, then f of z is said to be twice differentiable. Proceeding like this, we can find the derivative of an analytic function and so on. That means an analytic function is infinitively differentiable. This is the fourth definition. So, a function which is infinitively differentiable is said to be an analytic function. Examples: f of z equal to e raised to z is analytic everywhere. Such a functions are known as entire function. A function which is analytic, the entire complex plane or the whole complex plane is said to be an entire function. E raised to z is an entire function, and the radius of convergence of an entire function is infinite. That means in the entire complex plane, the function f of z is analytic. Then a point at which the function f of z is not analytic is said to be a singular point or singularity of f of z. For example, consider the function f of z is equal to 1 by z, which is analytic everywhere except at z is equal to 0. Z is equal to 0 is a point which ceases f of z to be analytic. Such a point is known as a singular point or singularity. Now consider another function f of z is equal to z divided by z minus 1 into z minus 2. Here z is equal to 1 and z is equal to 2 are singular points. That means the function is analytic everywhere except at z is equal to 1 and 2. So they are singular points of the function f of z. A singularity is said to be isolated if there exists no other singularities, some neighborhood of z0. Where all the singularities which we are considering are isolated singularities. For example, 1 by f of z is equal to 1 by z minus z0. Here z equal to z0 is an isolated singularities. Now, isolated singularities are again classified into three: removed singularity, pole, and essential singularity. The singularity which can be removed is known as removed singularity. For example, f of z is equal to sin z minus z0 divided by z minus z0. As a removed singularity, at z is equal to z0. To explain more detail the different types of singularities, we require the power series expansion of an analytic function. A function of the form f of z is equal to a0 plus a1 into z minus h0 plus a2 into z minus h0 etc. and the whole square plus etc. is known as a power series expansion of f of z about z is equal to z0. When z0 is equal to 0, then f of z becomes a0 plus a1z plus a2z square plus etc. And this power series expansion is absolutely convergent. If there is a number r such that mod z is less than r, that is the consider the circle mod z is equal to r. Within the circle, the function is absolutely convergent. Now, there are two other types of power series expansion. If a function f of z is analytic, which has a power series expansion, that is also an equivalent definition of an analytic function. The power series expansion is classified into two: Lorentz series expansion and Taylor series expansion. A function f of z which is analytic within and on a closure contour C, and z0 is any point interior to C, then f of z can be written as f of z is equal to f of z0 plus z minus z0 into f dash z0 plus etc. plus etc. അല്ലെങ്കിൽ we have f of z is equal to a0 plus a1 into z minus z0 plus a2 into z minus z0 the whole square plus etc. Such an expansion is said to be a Taylor series expansion. A function which is analytic in an annulus, that means a circular disk with a hole at its center, that means a region between two concentric circles is known as an annulus. A function f of z which is analytic in an annulus has the Lorentz series expansion, which has two parts. One is the real part and other is the singular parts. One is the regular parts and other is the principal parts. That is f of z is equal to a0 plus a1 into z minus h0 plus a2 into z minus h0 the whole square plus etc. plus b1 divided by z minus h0 plus b2 divided by z minus h0 the whole square plus etc. Here the second part, that is b1 divided by z minus h0 plus b2 divided by z minus h0 the whole square plus etc. is known as the principal part of the Lorentz series expansion. If the principal parts contains no terms, that means Vn is equal to 0 for all n, then z is equal to z0 is said to be a removable singularity for the function f of z. If there exists a finite number of terms, say b1 divided by z minus h0 plus b2 divided by z minus h0 the whole square plus etc. plus bm divided by z minus h0 the whole raised to m, where bm not equal to 0, then the singularity z is equal to z0 is said to be a pole of order m. When m is equal to 1, the pole is said to be a simple pole. And if there exists an infinite number of times, say b1 divided by z minus h0 plus b2 divided by z minus h0 the whole square plus etc., then the singularity z is equal to z0 is called an essential singularity. That means there are three types of isolated singularities. What are they? 1. Removable singularity. 2. Poles. 3. Essential singularity. For example, consider f of z is equal to e raised to 1 divided by z minus h0. The power series of e raised to 1 divided by z minus h0 contains an infinite times of negative powers of z minus z0. Therefore, z is equal to z0 is an essential singularity for f of z is equal to f of z at z is equal to z0. Earlier I mentioned the function f of z is equal to sine of z minus h0 divided by z minus h0 as a singularity at z is equal to z0, removed singularity. This function can be defined as limit z tends to z0 sine of z minus h0 divided by z minus h0 is equal to 1. Such types of singularities Such types of isolated singularities which can be removed by defining the function suitably is known as a removable singularity. Now, you consider an energy function and consider a function f of z is equal to u plus ib. Suppose that f of z is 70, where u is the real part of f of z and v is the imaginary part of z. What is the necessary and sufficient condition for a function f of z to be analytic? The function, if the function f of z is analytic, then u and v satisfy the CR equations. That is, dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. These are known as the CR equations. The function f of z is analytic, then u and v satisfy the CR equation. This is only a necessary condition, but not a sufficient condition. If u and v satisfy the CR equations, the function need not be analytic. Now, what is the sufficient condition? The function f of z is equal to u plus iv is analytic if and only if u and v satisfy the CR equations, where ux, uy, vx, vy, the four partial derivatives should exist and they should be continuous. CR equations are only a necessary condition for a function f of z to be analytic. What is a necessary condition? If a function f of u and v satisfy CR equation, the function need not be analytic. The function is analytic if and only if u and v satisfy the CR equation, the whole partial derivative should exist and should be continuous. This is the necessary and sufficient condition for a function f of z to be analytic. Now we consider f of z is equal to u plus iv is analytic. Then u and v satisfy the CR equation. Any real valued function u of xi which possesses continuous partial derivatives of the second order and satisfying the Laplace's equation dou square u by dou x square plus dou square u by dou y square is equal to 0 is called a harmonic function. Any real valued function which possesses continuous partial derivatives in the second order and satisfy the Laplace's equation dou square u by dou x square plus dou square u by dou y square is equal to 0 is called harmonic function. Example, if f of z is equal to u plus iv is analytic, then u and v are harmonic function. From CR equation we can easily derive that u and v are harmonic. U satisfy the Laplace's equation and also the partial derivatives are continuous. If f of z is equal to u plus iv is analytic, then u and v are harmonic function, and v is said to be the harmonic conjugate of u and u is said to be the harmonic conjugate of v, and they are said to be harmonic to each other, conjugate to each other. When we are given one real valued part or real function, a real part of the analytic function f of z, we can easily determine the imaginary parts.